Okay, young people, here is part 2 of the 4 guys gas laws. So we're going to run through the last 2 guys and talk a little bit about combining everything and see how that works, okay? So gas laws. Gay-Lussac's law, the first law, he talked about combined volumes. And basically what he said is when gases react together to form other gases, and when all volumes are measured at the same temperature and pressure, the ratio between the volumes of the reactant gases and the product's gases can be expressed in simple whole numbers. So there's always going to be a whole number ratio between them. This was the prelude to the molar relationship found in a chemical equation. So this is what they started looking at. Remember, they didn't know anything about particles when this was happening. So this was a really big deal because they started seeing that there were some relationships. For example, the one that I think the most of is the electrolysis of water, where in the container we see twice as much hydrogen being collected as oxygen because there are 2 moles of hydrogen for every mole of oxygen collected from the electrolysis of water. And so this is what they were observing, and this is what they were seeing, and this is why they were seeing it. Okay? Gay-Lussac's law 2 really had to do with temperature and pressure. And this is the one that he's known for in gas law speak, but the combined volume was what led Avogadro to his ideas too. Okay, so gas law speak says Gay-Lussac's law was the temperature of the confined gas is directly proportional to the pressure exerted on that gas if the volume is kept constant. So volume must remain constant here. He was a French chemist and he was a contemporary of Charles and Avogadro and Boyle. They were all really contemporaries. And they studied these relationships. He studied pressure temperature, whereas Charles studied temperature volume. And the reason that is because Charles was always using an expandable container where the volume could change because the container could expand. Gay-Lussac did not. So we get this P1 over T1 is equal to P2 over T2, or P1 T2 is equal to P2 T1. I find that a little confusing because you're going to want to do 1 1 2 2. So I would rather you remember the P1 over T1 is equal to P2 over T2 if you're going to remember anything. That seems to fit with what we understand because we know as pressure increase, temperature increase. So if they're going in the same direction, they have to be divided by, not multiplied by. So we have to really kind of think about that. So be really careful about that one. So this device right here is called some people call it an absolute temperature measurer. Some people call it a Gay-Lussac's apparatus. But what you will notice is that in this, we have a device down here that has this bulb on it. On the bottom, you see this bulb. I just need to use my marker here because I can't seem to get a pen to come up on this doggone thing right at the moment. So I see this device right here. Okay, that device right there. I'm not sure what's going on, but my touch screen is not working. Nothing's working. Okay, so you see the bulb down here that you can see by this. Let me just get rid of it. Laser pointer. Okay, here we go. Here's my laser pointer. This bulb. This bulb means that there's a volume that cannot change. This is a stiff structure, a rigid container. The volume's not going to change. So when I plunge that into really cold something, hey, the pressure's going to change here. If I plunge it into really hot something, hey, the pressure's going to change here. So if it's really hot something, the pressure gauge is going to go up. If it's really cold something, the pressure gauge is going to go down. Okay, get the idea? So Avogadro's hypothesis came from Gay-Lussac's combining volumes. He said equal volumes of gases under the same conditions of temperature and pressure contain equal numbers of molecules. And this is where the stretch came. And it's also why it's called a hypothesis and not a law at this point, because it didn't become law until much later. Okay, I'm also going to get rid of my face because I'm afraid that I'm covering some stuff. Sorry about that. Okay, so Avogadro was an Italian physicist. Yeah, he was a physicist, not a chemist. Amazing, huh? And he was using a paper published by Gay-Lussac to help him theorize his hypothesis. The problem was he couldn't define particles because the idea of an atom is just brand new when all of this stuff is coming down. So he was having a little trouble with this, but he had the right idea, which is amazing to me when you really think about it, that they didn't have an understanding of the particle nature that we have. but they had an understanding of the physical world that was surrounding them and what was going on there. So it's really amazing to me when you think about it like that. So here's an example of Avogadro's law. What he basically said was that as the number of moles increased right here, as the number of moles go up, what also goes up? Volume goes up. So if I add more moles to a container that's flexible, that volume is going to increase. And so we see these 4 containers with different gases. Well, what he said is that because these 4 containers are the same volume, at the same temperature and the same pressure, then they contain the same number of moles of gas. And that is what began the process of coming up with Avogadro's number. Okay? It was gases that did that. It's kind of amazing that we don't talk as much about gases because we feel like we understand them more, but I think that we don't have as great an understanding as we should. So Avogadro's law comes because the volume of a gas at a given temperature and pressure is directly proportional to the quantity of gas. So temperature and pressure are the same, volume and number of moles are changing. So we get this expression that V is proportional to N and N is proportional to volume at constant TMP, temperature and pressure. So we get a formula, N1 over V1 is equal to N2 over V2. And you'll notice these formulas look the same. Why? Because Charles' law, Gay-Lussac's law, and Avogadro's law have the same relationship. Those relationships are direct. If we keep one thing constant, all the other relationships are direct. The only one that's indirect is Boyle's law. Boyle is the only one that has an indirect law, and you notice they're multiplied by each other. So it's really important that you kind of keep that in mind, that direct and indirect have a different relationship mathematically as well. Okay, so this is another question. Suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all this O2 were converted to ozone at the same temperature and pressure, what would the volume of ozone be? So I'm going to let you work through that problem and bring your questions in tomorrow for me. Combined gas law. Now, this is the fun part because we use the combined gas law more than we use the individual laws. We can use the individual laws when we're only looking at 2 particular things, but most of the time we're looking at temperature, pressure, and volume at all times. And sometimes we even throw in moles, and we're going to be talking about that one in the next set of notes, okay? We'll get to the mole thing in just a minute. Other than Avogadro's, the combined gas law doesn't talk about moles. So you start with the combined gas law, which is P1 V1, P1 times V1 over T1 is equal to P2 times V2 over T2. Hey, hang on, that looks like the same thing that I just did. I just combined it all together. That's because that's exactly what it is, okay? Exactly what it is. You'll notice V1 over T1. You'll notice P1 over T1, and you'll notice P1 times V1. So you have all of the relationships, excuse me. I find that this is the combination that I remember the best and understand the best. This one is exactly the same, except that I've done some math to get them all multiplied by each other. So you memorize a simple pattern to figure out the rest, okay? So place the chemist's name in alphabetic order. That's Boyle's, Charles, Gay-Lussac's. Okay, there we go. Boyle's uses the first 2 variables, P and V. Charles' law, the second 2 variables, that's V and T. And Gay-Lussac's is the remaining combination, that's P and T. So they're saying if you have it this way right here, that Boyle uses P and V, the first 2, Charles uses V and T, the second 2, and then Gay-Lussac's is P and T. I kind of look at it like this. PV on top is Boyle's law, VT is Charles' law, and PT is Gay-Lussac's law. So any way you want to do it, just make sure you can understand this and you know the relationship. So whichever variable isn't appearing in the formula has to be being held constant, which is why it doesn't appear in the formula. Okay, that's the end of this set of notes, so hopefully you will be just fine and dandy. See you tomorrow.